And we're live. So welcome everybody to the advanced TLC topic of machine learning. Our guest expert, can we call you an expert? I think you should take the title, is Matt Gershoff. He's not new to the TLC. For those of you who joined the Journey Analytics conversation a while back, Matt was one of our guest panelists, and we wanted him to come back because he's super smart and knows all about everything related to machine learning. He's the co-founder of Conductrix. I did a great job with that. Anyway, you should check it out. It's a great tool. I'm sure it will actually come up in conversation today. He has 2 masters in resource economics and artificial intelligence. And he spent his 90s working in database marketing, which is basically what we all call data science. And I put this in here because it's Michael Helbling's joke from the DA Hub that we all adored, which is, what is a data scientist? And it's basically a web analyst who works in California. But that's not true for Matt. He is a true data scientist. He knows his stuff, and I really look forward to this conversation. So welcome, Matt, and welcome, TLCers. As a reminder to those of you on the call, if you have specific questions, feel free to go off mute, ask them directly. You can ask them in the Zoom chat, or you can join the TLC Slack. There's a channel now called TLC-calls that you can join, and we'll have side conversation going there as well. So whatever works for you, feel free, ask your question. Especially with this topic, a lot of questions are really specific, and Matt's happy to help answer them in any way he can. So let's get started.
Sounds good. Thanks for having me, Kelly.
Thanks for being here.
And I just have to say, though, I don't really consider myself a data scientist. I think I'm too old. Like, there's like, I think you got to be under 40 now to be a data scientist,
or to at least to use the label.
Yeah, that's a new term then. And I'm not a great programmer, and I think you got to probably be a pretty good programmer to be a data scientist. But be that as may, I'm totally excited to be here. Thank you so much for inviting me. And yeah, what do you want to talk about?
Well, I think the most reasonable question to start with, and the one that I got the most frequently for those of you who sent in your questions early, is how do you define machine learning? Like, what is it? Are there different types of machine learning? What are we talking about here overall?
Well, it just so happens that I might have some slides that we can walk you through.
I am shocked.
Yeah, I know, shocking that I prepared a little bit. But let me just see if I can figure out how to share my screen so you don't have to look at my
bottom
face.
Center button that says share screen.
Yep. Okay. Can this be seen right now?
It can.
Great. I'm going to do this a quick slideshow. And I promise this won't be like a whole class in machine learning, but I think it is useful. I think it is useful just to have like a basic understanding of like kind of what we're talking about with machine learning, and demystify it. A lot of times, machine learning and AI right now, especially in the popular media. I mean, I know a lot of you folks are pretty sophisticated and already probably grok this, but for some of you who are new to this and you just want to get a good understanding, there's a lot of hype in the media, and I think it's actually quite helpful to just have a basic understanding. And I'm not gonna. It might sound like I'm being negative about things. I mean, that is part of my personality, but I think it is useful just to go into things rationally and not ascribe sort of magical capabilities to machine learning or AI. Okay, so it's really underneath the hood. Usually, most of the systems are using fairly simple components, and it's really how they're composed which gives them a lot of the power often. So a lot of like the low-level things actually are pretty accessible with a little bit of legwork. So machine learning. So let's start with computer science. And computer science is the study of like programs. So we kind of want to understand like there's complexity theory and sort of like how the algorithms work. That, when we write a program, how might that work in general? Not this particular program, but a program that does this type of thing, right? That maybe counts or sorts and you can kind of have some sort of statement on how it might work. So it's like the study of programs that people write, right? Something that's going to be executed on a computer. Statistics is really the study of how we make inferences from data and observations, like a high level, right? And machine learning is Waldo, right? So it's in the middle. So it's this overlap between making inferences and learning from data and observations and computer programs, right? So basically it's constructing computer systems that can automatically improve through experiences. And this is from Tom Mitchell. And I can give Kelly all the links. So if you want to read up the original sources and not just take my word for it. This is from his new book. But I think this is a useful way of thinking about it. It's the output of machine learning often is really a program. And so that's an artifact from this process that we can evaluate, right? So if you think about the output as a program that's going to execute, and maybe it's a little targeting program, or maybe it's a program that is assigning, like what image, it's a cat or a dog, right? Or what's in the image, or speech recognition. So you're going to put in some speech files, and then you're going to get out some sort of interpretation and understanding. Those are programs that have been learned from data and observation, as opposed to having a person like write out that program. And that's, in certain contexts, it's much harder to try to figure out how to write that type of program than just to learn it. And that's really machine learning. And you can have a very simple procedure to get you a program that might actually be effective. So it doesn't have to be complex. And in fact, really what we want is to use the most simple program or the most simple machine learning possible in order to execute on our task. So I don't know if there's any questions around that, Kelly, or you think that's pretty clear, but that's the idea. Machine learning is really this process of really generating and automating a program that's executing on some particular task. We have some sort of problem that we're trying to solve and that we want to automate.
No questions yet.
Sounds good. So let's just quickly go over the different types of machine learning. And it's generally, they're classified in three high-level approaches. There's unsupervised learning, there's supervised learning, and then there's reinforcement learning. And reinforcement learning is, up until maybe a few years ago, was sort of the neglected child of machine learning. Usually when the discussion about machine learning was usually the first two. But reinforcement learning is especially with AlphaGo and some of the work from DeepMind is starting to percolate up into the consciousness, I guess, of the general popular domain. So unsupervised. An example is cluster analysis. A lot of this stuff you're already familiar with. And that's the other thing. A lot of these methods and approaches people were already using, and now just the term machine learning has gained a popularity. And so a lot of this is not new, right? So don't be surprised if this seems, particularly, unimpressive and it's not the magic that you're expecting, but this is what it is. And so cluster analysis is, let's say we have stars. So here's like an example. There's stars in the sky, and each one of these stars is like an individual observation. And we might believe that actually stars, there's some latent structure. There's some additional way of understanding how we can categorize the stars, right? And so in some sense, some stars may belong together, right? They're grouped or clustered together, and other stars might be grouped or clustered somewhere else, right? So cluster analysis is kind of like, or is, trying to find the galaxies from the stars, right? And so if you think about when we look up in the sky, each star is like, it could be analogous to when we're doing some sort of customer analysis. Each one of the stars is a customer, and we might want to say, well, actually, some customers are more like one another, and other customers are less like those and more like, some other group. And so we can kind of think of it's like we're trying to extract the galaxies, right? We're trying to find the galaxies just from the stars. And so that's a cluster analysis. Now, remember, when we look up at the stars, there's no one telling us what's a galaxy, right? So in a way, we're using the information about how the raw data is distributed to infer some additional structure that we believe has generated this data, right? So we believe that there's some additional structure like a galaxy that's underneath our raw data, like our unique data. So we're trying to discover this, but it's in a way sort of a definitional problem. It's like we're looking at the data to kind of define the structure. It's not like we're being told what to look for, right? So if that's, I don't know if that's clear, but maybe when
Makes
we
a lot of
talk about
sense.
supervised, we actually have an answer for the data, right? So we have our input data. So maybe it's like customer data, and then maybe we have whether they bought or not. Or maybe it's a set of pictures and they've been labeled whether or not it's a dog or a cat, right? Or a bunny. So a classification problem is trying to assign a class, right? Or a topic to like news. What type of topic is it in the, got all these news articles and, what's the topic that's most appropriate? Or maybe it's, the bunny or the dog. And regression is just, we're trying to find a score. So regression might be something like, what's the predicted, revenue from this particular person. So it's a numeric value that we're trying to predict, right? But the idea is that we already have for some subset of the data the actual result, right? The true result. And this is usually people talk about this as like there's a teacher, right? The teacher knows the true answer, and we're the student trying to learn. We make a guess, and the teacher tells us how far off we are. He tells us if we're wrong or right or not. So like, as I said, an example would be, say, image recognition, right? But this is the type of thing where we might use predictive targeting, like a targeting problem, and we're trying to target, a particular user to whether we mail to them or not, or to give them the offer or not, or which experience to give them, right? That's sort of a supervised learning problem, assuming we already have the data. Now, reinforcement learning is we're trying to learn a policy, right? So we have this problem where we don't have any data up front, and the only way to collect information about the problem is to actually interact with the world or the environment, right? So it's either we have to play the game and see whether we win or lose or not. And instead of knowing and being graded on how well each action we take, right? There's no teacher that's saying you did a good job. You just get a reward. And so reinforcement learning is really an idea that machine learning has sort of taken from psychology, if you think about it, and with sort of operant and classical conditioning, where just with like Pavlov's dog, you're training the dog or you're training someone not by instructing it, but by giving it a reward. So when we want the dog to sit, we don't like show the dog how to sit and articulate, oh, you're doing it wrong. It's just when the dog finally sits, we give the dog a bone. So it gets a reward. And that's what reinforcement learning is. And that's kind of the bandit problem. So you probably heard about multi-armed bandits. Multi-armed bandits sit within this reinforcement learning because we're just trying things out in the world. Like we're trying out the different offers or the different experiences. And then we're seeing what the conversion rate is. That's the reward. That's the bone. And we're going to start to learn which action to take based upon which action gives us the most bones, right? So there's no...
And the bandit problem is what many of the out-of-box testing tools are using today. That's for any kind of auto optimization.
Yep. So the bandit is really, we're trying to like automate the process of taking a selection. So it's slightly different than testing, or it's a different objective, or we're really trying to, learn as fast as we can what the best policy is, right? So we're trying to teach the dog, and in this case, the dog is our campaign or our website, right? And it's trying to like figure out what the best action it should take in, which is slightly than like a hypothesis test. They're different objectives, even though they seem similar, and they're doing similar things.
So there's drawbacks. Anytime that you're letting the machine do that, there's got to be a pull and a give and take between accuracy and interpretability.
Yeah. So surprisingly, I don't know how this happened, but
I swear I didn't look ahead.
Uh-huh. Yeah. So this is really more for like when we're, when people are right now, I'm not sure why, but there seems to be some folks are pushing analysts into like deep learning and AI, and it's sort of like a panacea for optimization and for analytics, and everyone's gonna lose their job, and it's all gonna be automated. And that actually is not. I don't believe that to be true at all. Actually, I think that's based on a faulty understanding of the types of problems that we face in marketing versus the types of problems that are being solved by deep learning. And I'll go into that briefly, what deep learning is. But like there was a lot of activity and a lot of excitement when Lee Sedol, who's a Go master from South Korea, lost to Google's DeepMind with AlphaGo, right? Lost 4-1, I think, in some competition. And the reason why that was such a big deal is that actually Go is orders of magnitude more complex than chess. And so it's always been a problem that the AI researchers for the past, since the 90s, I know, and maybe even earlier, have been trying to crack, right? But it's a very complicated problem. It sits in a big space. There's I think as many game board positions as there are atoms in the universe, or at least that's what people hype up, is that's being a big deal. But I think it's important to be able to assess, especially as analysts. I think our main job is not about solutions or methods. It's really about assessing the problem and assessing the environment in which the problem lives, right? And seeing how similar is this, or what is its nature. And so what I mean by that is that like AlphaGo is a problem in which we have to make decisions. There is a reward, right? We either win or lose, and you can think of that as like a conversion event, right? So that's similar to the types of problems that we have in marketing, right? Because the decision, where we're putting the game piece is like, what offer we present, or green button, blue button, or what product features to include, right? Any of those things, any of those interventions that we're trying to see if they increase the performance of our website or our call center or what have you. It's a sequential decision problem, right? Which I think is useful to think about. Attribution is when we have sequential decisions, right? So I'm going to put this piece down, but I don't get rewarded. I get rewarded at the end of the game. And so there's like a trajectory. There's a sequence of decisions that I'm going to make. At each step, I do something, and then I'm going to have to do another thing, and then another thing. And then I have to figure out how to reward all those moves. In order to know how good a move is, it's going to depend upon the context and what I do in the future, right? So I have this whole a system of decisions I need to make, a sequence. And that's really what attribution is in a way, right? So let's say you're doing an intervention on the web page, and maybe if there's the call center, and maybe in the mobile app. And if you think about it, it's the same type of problem. So we do have marketing problems that also have this sequential nature to it, right? And that's where some of that reinforcement learning comes in. That's in the AlphaGo. But where it's different is that there's sort of perfect information about AlphaGo. We know when you go and play Go, you know what the moves are, right? You know what a valid move is. And you know how to find the end of the game. And you know if you go back to play Go next week, it's the same game. Like nothing's changed, and there's no noise in the game, right? There's not like any uncertainty.
It is in fact finite, even though the volume may be huge. It is still, there are a finite number of moves if you follow the rules of the game, whereas not the case in reality.
Well, in marketing, it's just we don't have a deterministic. It's one, we don't even know if what we're doing makes any difference. Like if you think about it, if we're playing Atari or a video game, we know when we move the controller, the person's, the icon or the avatar is going to move left or right, and if we shoot, a bullet's going to come out. And we know.
You just aged yourself.
Yeah, I don't play video games. I used to play Minesweeper actually, which is totally depressing game. But right, but we know it's a solvable problem because we can solve it. You can go play a video game and you understand quickly how to play the game. Whereas when you're playing a video game, the price of Bitcoin does not affect how the game plays, or the temperature outside, or the day of the week, or all these other external factors that are not contained within the game are not altering the payoff of the game, right? Or how you move. Whereas in marketing, it's especially in optimization, and since that's what we're talking about here, it totally does. And in fact, we don't have a closed system, and we don't even want. So one, we don't even know what context or targeting features make a difference. But also, we don't even know if our interventions make a difference. So, I mean, I'm sure a lot of folks here, especially because of the topic of your of this web series, everyone's run A/B tests, and everyone's run A/B tests that there's been no real result, right? It's like there's no conclusion to be made. Everything looks like it's performing basically the same, probably because everything is performing the same, which just means the different alternatives do not. If you think of the different alternatives in your A/B test is like your game controller, like your joystick moving left and right, up and down. Those are 4 options. It doesn't do anything. It's in a way the joystick has no effect, right? And that means there's often a lot of noise in our problems. That makes marketing problems a lot more difficult because we don't even know what we're both defining the game and trying to learn how to optimize it. We have the joint problem. And I think because of that, it makes it unlikely that porting over a very complex model like deep learning is really going to give us anything, number one. Number two, a more complex model like deep learning is very difficult to interpret. But unlike AlphaGo, where we don't need to know how the game is being played to get adoption, right? To get the organization to approve it. For us as marketers, you do need the rest of the organization to get approval, right?
So to get their buy-in.
Yeah, for buy-in, for trust, right? For insights. GDPR is coming up. And so there's regulation around automated systems, Article 22. And so even if you're not in Europe or you're worried about, your European customers trying to sue you, you might have data governance, you might be in banking or in finance, and there's, rules against discrimination and redlining. And so you might want to have to audit how your automated system is going to work. And if it's a very complex system, you're not going to know for any input how it's going to output. But if it's a more simple model, there are certain interpretable models, and we can go over that. Those are more amenable to all these other objectives. When you're trying to solve a problem, it's not always just about one thing. It's not just about whether it's accurate enough, right? It might be, it has to be simple or it has to be interpretable. It's just like when you go to a restaurant, you don't always, sometimes you definitely want to have the best meal, right? Like I want to have the very best of sushi, right?
Well, you don't want the worst.
Right. Well, you definitely, but and of course, you want it to be, ecological as well. So sure. No bluefin tuna. But other times you're going out with friends and you want to vibe. So the food doesn't matter. It's just you want it to be, we're a place where you can hang out and get a variety of things, and you can bring a variety of people, and you might have different objectives to it. It's not just about the quality of food. And that's a good thing to think about here with when you're thinking about different models. It's what's the bundle of goods that this type of approach gives you, right? And so some approaches might give you greater accuracy. Other approaches will give you a bundle of some good accuracy as well as interpretability.
And if you can understand it, you can scale.
You can understand it, and also you can ensure that it's you can debug it. If you remember, we're talking about machine learning is outputting a program essentially. There's like easy to interpret code, and then there isn't. And really, just because you're generating some machine learning doesn't mean that the data that's gotten in there isn't junk. So let's say you have a model, and it's saying everyone who's who's come in on the weekend, we should give a particular product offering to. But that can't, you see like half the people are coming in on the weekend. But that can't be right because half of your customers don't come in on the weekend. Really, you only have 10%. So you can quickly see, well, actually, there must be a data problem because the model seems to be thinking that half of the users are coming in on the weekend, but we know for a fact it isn't. So we can go and debug this thing, right? So if it's interpretable, you can debug.
Does machine learning control for the problem of correlation is not causation? Or is that where the
Uh,
business analyst comes in and says, no, yes, those things happen concurrently, but they're not related?
well, no, most machine learning would not, any predictive modeling, it's really reinforcement learning a little bit, right? Because when we're using unsupervised learning, we've collected the data in some way, right? And we're just trying to clump the data, right? We're trying to find objects and artifacts in the data, right? So we might want to classify like news articles, or we might want to classify our customers. With the supervised learning, yeah, there is no claim that can be made that you found some sort of causal structure, right? Because you can always inverse the relationship.
Right.
With the reinforcement learning, though, it is a little different because we're selecting the controller. We are selecting the intervention. With the predictive targeting or the supervised learning, the data already exists and it's been collected in a certain way. But when we're doing RL or the bandit or something, there's two types of data. There's the data about the user or the context, right? And then there's also the data about our actions. So we're actually making interventions into the environment, right? We're taking action. So in a way, actually, there is some causal information there, right? Because I'm actually altering. I can take action A or I can take action B, and I can see the marginal difference between taking action A or B. So there is some sort of causal structure with reinforcement learning methods, because we're doing something. We are taking action in the environment. We're kind of running there's some aspect of experimentation embedded in the learning process.
That makes sense.
But there are some cost interpretability. Usually, like accuracy can suffer. So, for like AlphaGo, you wouldn't want a simpler model or interpretable model, and because it just wouldn't have the power to express the deeper, complex sort of nonlinear relationships that exist in the game state. But for something like predictive targeting, you probably don't need something too complex. So what I mean by interpretable methods, linear regression is interpretable. I don't know if this will work. Yeah. So like all this is saying is that we have a relationship between our input data. This is our input data here, right? So this is like our user data. So weekend, maybe, purchase amount in the past, amount, right? You get it. Mobile, they're on a mobile device. And then this is how much, these are the weights, and this is what we want to learn. So this is maybe the impact on our prediction of weekend. So how much, if it is on a weekend, how much do we alter our prediction, right? And past purchase amount, if we increase purchase amount, this tells us whether or not how much we alter our predicted value. This is like, probability. Maybe this is the probability of buying here, and we're trying to predict this, right? And so these weights here are interpretable as the marginal. That's too complicated. These weights are like how much the probability to buy will change if they're weekend, or how much will the probability to buy change if we know the purchase amount. Another approach is decision tree, and I think this is actually the best approach because it's very simple, because the marketers or the account team can easily understand this thing, and it basically you just read it off. It's like, are they a rural customer? Yes, then A is the right answer, right? So we offer them A. If they're not rural and they're on a mobile device, also get A. If they're not rural, not mobile, and they're registered, give them C. And if they're not registered, give them B, right? And so you can see this policy, you can see exactly what the system will do, what it will select. You can ensure that this is okay. So there's no data in here that is not compliant or is not under your governance or is discriminatory. And you can also log this, because I can just say, well, this guy here, this one here, I should say, I can, when I make the decision, I can also ID this rule. This is essentially a rule, and I can log that when I make this decision. So if this user comes back and says, hey, why'd you give me B? You can just read this off. You can say, well, because you had these attributes, and that's why we picked B for you. And this might be useful, especially if you're in finance or credit scoring, and you do have European, you're doing stuff with the GDPR. You can explain, and then the EU citizen can decide whether or not they want to contest it. But you will have at least met your requirement to explain why you gave them a decision, right? So as I was saying, decision trees have like these nice properties. They're human readable for trust and insights, both, right? So you can actually learn from them pretty easily without having to like look at a matrix of weights. It's easy to audit just to ensure compliance, right? And they're loggable, right? So the tree is really a set of decision rules. It's compact. It's really easy. It's less complex. So it's just like another piece of content. So it's like a logic content that's mapping data to experience. And as I said before, you can just log the thing. Is that clear, Kelly, or should I?
It is. I want to address the one thing that we discussed. Oh, I see you, Dylan. Just 1 second. I'll give you your thing. But as a placeholder, one of the things we talked about was how we could use A/B testing, our traditional testing, to evaluate the accuracy of these models, whether it's decision tree or not. But I want to let Dylan ask his question first. I just want us to remember to get there, because that was what question somebody sent us. Go ahead, Dylan.
Yeah, you mentioned that a decision tree is human readable. While yes, it is human readable, you may see that somebody likes this IP octet range of this versus this. It may actually be the case that they're using a mobile device that's using that particular IP range. And so how do you bridge that gap of the human readable, the decision tree identified this piece, but what it really means is this other variable over here?
So are you asking that there's confounding, or is it a question about the multiclinearity? Is it that we're using? I'm not sure I understand.
You have to use a big word so he understands, Dylan.
Yeah. No. Okay. So the features that you feed the decision tree, the features that are available to be able to make the decisions on, may be inaccurate for describing the actual features that are driving the differences across the impact of the experience on the particular cohort. So, for example, you have IP address available, and that comes up as something that people in this IP address range are actually affected differently by the experience. When in actuality, what it really is, it's not the IP address, it's the fact that they're actually using a mobile device, right? And they're on a train. And so the fact they're using a mobile device and on a train, that actually is the real reason why the experience is happening. And so how do you get from the feature that's showing up that is human readable, kind of, to the real meaningful feature that is actually driving the variance?
But do we yeah, that's a good question. I think it's sort of addressing a separate issue, which is, do we have, so you're saying, do we just have IP addresses, or do we also have the mobile and they're on a train? Like, are we missing something?
So for this example, yeah, you're missing some data. So for example, font size might correlate with age, and the better that people with a higher age will react to the experience, right? That's another example of a latent variable that's not being measured correctly. And so how do you get to that point where that's actually the real difference, not the piece that, oh, the machine identified that the IP range or the larger font size is really driving it?
Yeah, well, if you don't have that data, again, that's the problem. I don't know how you would do that, especially if you don't have, so that's totally true. So this mapping is going to be based on the like the data that is fed into the solution. So independent of if it's a decision tree, and just to be clear with everyone else, because I know you're aware of this, this question is like true of any of the models, right? So it's independent of the fact that if we're using a tree or a net or regression or whatever, if what we're really using is a proxy, right? In a way, the IP is acting. There's a spurious relationship, right? Because it's really underneath the hood. It's mobile and it's on the train, maybe. But in a way, if it's just for prediction, it may not matter, especially if that relationship stays, right? And in a way, it's also related to Kelly's point about causality and correlation, because we don't know.
No, I was going to get to. I understand that it doesn't matter really for the machine to be able to make the prediction, but it does matter for being able to feed insights back to the team in order to be able to build better experiences.
That's right.
So that's the challenge.
Because you can't go back to them and say these IP addresses matter. That won't mean anything. You can't make any decisions based on it, but you could go back to them and say mobile devices and people on a train respond more positively to this treatment over that.
That's right, and that's why this isn't that's why I don't think that the world of somehow this notion that deep learning or AI is going to come in and eradicate every analyst's job is a valid one, because what Dylan is saying is that you need to have someone give it like, does this make sense? So, but what you're also saying, Dylan, is that you would look at this tree, because I think actually the decision tree is exactly what you would want in that case, because you would look, and you, smart guy, right, who understands the data that you're looking at, would see a node that's splitting on IP addresses. And you'd think, well, why that's probably related to something else, right? That's probably not a true relationship. Why would it be that you would want a reason? Because IP addresses are something that have no intrinsic meaning to them. And so it must be that for whatever reason, these IP addresses are actually a shadow of something else, right? Like that would tell you, that's why the tree would be good, because that's like a debugging. I don't know. There is no answer though. The only relationship that the model is going to be able to extract is going to be conditioned on the data that's added into it, right? So why would you be giving, I would turn around and say, well, why were you feeding it IP addresses, right?
It's easy, right? But you're answering the question, and
like you're smart. Like that's the thing. That's why machine learning isn't a substitute. It's a complement, especially for marketing, especially when there needs, like, it's not something that is like, you just shove crap in and then just magic happens. Like it's hard. It's very hard. And this because of these tools doesn't necessarily make this process easier. It just makes it potentially have more efficacy, but it's not a panacea. And so Dylan is totally right. You wouldn't know. But then again, why would it have IP addresses in there? Someone somewhere wasn't thinking about what might make sense, right?
Oh, I couldn't get it instrumented. Yeah.
Yeah, or they're like, yeah, I know this isn't it, but there might be some sort of structure, and then you could go back and say, is this just spurious, or maybe this is insightful, and these blocks might mean something, and I'll go look and see where these IP blocks are coming from. Maybe they're from big organizations or something, right? And then you would follow on. So it's not one and done.
Yep, and so I think this leads really nicely into the question that Kelly had about, so how do you evaluate the efficacy of machine learning, right? When you're using A/B testing.
How do you use A/B testing to evaluate how good your model is?
Yeah, you use A/B testing. So A/B testing is like experimentation. It sits outside. Machine learning is really about like prediction and estimation, right? And we're trying to like build a policy. It's almost like constructing a hypothesis. We think this program is going to do well on our task. It's going to do better than random guessing, right? Or it's going to do better than us writing the logic ourselves. By that, in our domain, that means writing out business rules that we, the domain experts, think are going to be useful, right? So Dylan may think that being on, we have, let's say we do have the data about being on the train and being on mobile. And so Dylan says, well, I have a good idea, I have pretty good editorial understanding of the problem. And so those users should get this particular experience. And people who are, in a car should get some other experience, whatever it happens to be. And Dylan sits down and works on that for a week or a month. And then that is the targeting policy that you wind up using. Conversely, you could use some machine learning and try to learn what those rules are, right? But regardless if you're doing it as the expert who's writing it out or you're using machine learning, you still want to assess its efficacy. And so what you can do is just think about the program, whether it's written by the person, by people, the domain, or the machine learning. That's almost like another arm in an A/B test, right? So you just say, how much return do we get on average when we use this targeting logic to give our users experiences versus if we just randomly assigned them to experiences, how much lift? And so really you can think of like the A/B test or hypothesis testing is about testing the hypothesis that our predictive targeting has greater efficacy than, say, random, or testing the hypothesis that our predictive targeting has greater efficacy than if we just ran an A/B test and picked the single best option. And so really what you want to do is in market, regardless of the accuracy measures you get when you build the model, right? Or if you're using a Bayesian approach, like we actually use Bayesian approaches for our prediction, but we don't use Bayesian approaches for our hypothesis testing, right? Because we believe that Bayesian approaches are better for a variety of reasons that we don't have to get into, for estimating and sort of removing some of the overfitting that can happen, or the sort of false positives that the prediction can come up with. And hypothesis testing, a frequentist approach, is good for trying to refute. It's like a test. Like a hypothesis test is like when you take your final exam, right? And it's a really hard exam, and you pass, right? Or certain people pass and certain people fail, right? And it may very well be that not everyone who passes understands the material, but most people who pass probably do understand material because it was a really hard test, right? And it may not be that everyone who failed didn't understand the material, right? So that's the same thing with hypothesis testing. You're actually, it's like taking the final exam. And the harder the exam is, the harder it is for, the hypothesis that you understand the material, or the hypothesis that our predictive targeting is better than just random, is less likely, right? And so really what you want to do is in market, even after you've done all your analysis and you build your targeting, or you build your cluster analysis or your unsupervised learning, and you're using it somehow to make a decision, you want to see, if you didn't use it, how much worse would you do, or how much better are you doing with respect to whatever your objective is, using the machine learning versus not using the machine learning, right? And that's like this, what this is showing here. It's like an A/B test where we have our normal A, we have our normal B, and we have our normal C, but we also have this extra arm in here, which is all of the users who are selected under a targeting module. Here, these are all the users who are still randomly selected. And so what you want to do is a split test. And some of your users you'll assign randomly, right? And other users you'll assign using your targeting rules. And this could be using your machine learning, but this is the same type of thing actually you should do. Forget about machine learning. You should do when you're using business rules. Like maybe the business rules don't have much return, right? And then you can assess, well, how much extra return do I get from using our predictive targeting over just randomly selecting, right? Or we could also do, well, how much extra do we get from our predictive targeting than if we just pick the single best option, right? It's almost like, like predictive targeting or machine learning or even business rule targeting is cost. It's this extra complexity. It's all this, potentially extra places for it to fail. We have to have this model that we had to learn. We have to keep the model so that we can assign different users to different experiences. Maybe we have to retain all the information for governance or GDPR, whatever. It's an extra cost. It's a hassle. And so you want to make sure that's worth the hassle. And so let's say in the predictive arm, you got a return, and it's not that much more than random, or it's not that much more than a simple A/B test would give you. Then you might say, well, yeah, maybe it's giving me some lift, but it's not enough to be worth the costs. So you just fall back to the next best option, which would be just a simple, everyone gets the same experience, everyone gets B. Or it could be, and then you fall back again, you say, well, actually, does it matter between A, B, and C? And it's usually, like in a case where there is no result, you could either just pick randomly, or you could pick any one of them randomly, or if you wanted to reduce your risk, you could just always just randomly assign everyone. You wouldn't do that, but you could. Does that answer the question?
I think so, but you started going on to the path of talking about the costs of machine learning. And earlier when you and I had chatted, we talked about ROI in particular and how there are different costs associated with doing this manually versus using a machine to determine who to send what. Can you unpack that a little bit more and kind of talk to them about how you might think about this? Because the example you just gave was about the cost for machine learning, but there are also costs for the manual business rules version.
Yeah, and so it might be, sometimes, it may be that the machine learning the expectation that the machine learning is going to be something that you're going to audit. It's like automation, and so you think that you're hoping, your expectation is it'll do better than, let's say, your manual. So you're doing manual targeting, or you have some sort of manual process, and you want to automate that. It may be that actually, even if the machine learning approach, the automated approach, performs worse than your human curated selection, it still may be worth it depending upon the problem. So if the cost of human curation is quite high, right, and the automated approach with machine learning is quite low relative to the cost of the human curation, it may be that even if it's less accurate or it has less efficacy, it could still have greater ROI because the cost is much lower. But that's obviously going to be dependent upon the type of problem. So it's almost like, you have true customization, right? Sort of a boutique experience, and then you might have like a mass customization, which would be like with the machine learning often. And then you would just have sort of just the mass experience, which is what you get out of the A/B test. And it may be in certain circumstances that the human curated approach is the best approach and it's worth the cost. And it may be in other approaches where actually sort of the mass customization, as an analogy, is really the best way to go. And in other cases, it may not even have any real lift, and you just do the simplest thing possible. So really what you should always be asking is, like, what's the marginal benefit of this additional complexity? What's the marginal return that I might expect to get from doing this work? And what you want to do is think about, you always use random as the baseline, and you can have some idea of my conversion rate right now, or the return that I'm getting right now is 5%. And then you might want to do some sort of, best case scenario. Well, if I knew perfectly how to assign my users to the experience, what would I think would be my best case scenario? So maybe it's like a 10% conversion rate, right? If I was able to assign everyone to whatever experience they most prefer that I'm selecting from. And then maybe sort of a worst case scenario where it doesn't, like, what the payoff is, like, how much more do I get if I assign the user to the best one that they want versus the one that they don't want? And then you can kind of figure out, in the best case and in the sort of the lower bound, is this even going to be worthwhile to go forward, right? So it's just kind of sizing the opportunity, I think, is like a key thing to think about, as opposed to just, jumping into machine learning. We had an experience, I think I mentioned this before, with, partner who wanted to do sort of targeted bandit approaches for headline testing. And I asked them, and they were using our platform and running, and they were getting lift. It was like, 50% lift or something, 30% lift, doesn't really matter, but some sort of positive lift. And I asked them, well, huh?
It matters to the business.
Yeah, no, of course. But I asked them, I said, well, there's all this cost and this overhead to doing this. And I said, well, what is the value of an additional click? And it was like it was something lame. It was like a penny. And so in like 2 minutes, I just did a little calculation. I said, look, you're going to have to get like 600% lift in order for this to be worth it. And there's no way, just think about it. There's no way you're going to get 600. It's not going to increase six by a factor of 6. So don't bother. It's not worth it, right? The information, which is
I'll go and quit now.
No, no, that's not. No, the value of the analyst is doing that analysis.
Yes.
To prioritize where the work goes. If that wasn't the case,
lever is the right lever.
Yeah, if that wasn't the case, then if this was easy and it didn't matter what the context was, then what some other folks in the industry are saying, you would be out of a job. But I don't think it is easy, and I don't think our jobs are Our main job is to understand the problem, to understand the task, and to understand the environment. And then, conditioned on that, think about what the best way to solve it is. It is not to come in and just looking to apply a particular method, right? It's not to say, I'm really excited about trying out, using a saw and then trying to figure out where you can use the saw. It's like, I have these various problems, and then I'm going to decide whether or not I should use a hammer or a saw or whatever.
That's really, really important, because I did get several people asking the questions, when do I know I'm ready to use machine learning, or when is my company ready for machine learning, or how do I know when to use machine learning? And what you're saying is, you don't start with, I want to use machine learning. You start with, what is my problem and what is the right tool to address that problem?
Yeah, what's our level of sophistication? Is the organization even able to take action based upon the output, right? Like, does it have the, are you even there yet? Actually, not to put Dylan on the spot, but he would probably be the best person to answer that, because, or better than me even, because, he's had that experience of being in an organization and building out internally some of these capabilities in an organization that maybe didn't have this to one that does. And so, his insights, sorry to put Dylan on the spot there, but
no, it's fine. It's fine. I agree with you on it doesn't make any sense to the example that you had on the banner display component. Doesn't make any sense to run this, but I do think that there is value in bringing machine learning and this predictive intelligence and this technique into the organization. And while it may not pay off with the first time, but you may be trying to build a competency. And so figuring out how you go from a bespoke kind of integration to like a massive scaled integration, it's going to be, the cost isn't going to justify itself. And originally it needs to actually work its way up to it. And so you have to have these little bespoke ones to really get fuel to do this. If you just did the calculation of how much time it's spent to engineer all the data to go into the system to be able to have accurate predictive, it wouldn't pay out. It wouldn't even show to pay out for the first probably 3 or 4 experiments, right? Until you got to a larger scale. Yeah.
But Dylan, didn't you guys already have the ability to affect change in the infrastructure, right, in the organization? Like you were I meant.
It does exist. It does exist, but in the very beginning, it was very bespoke, right? It was very one-off. And so the amount of cost that it took to be able to do something like that, even just to hook up the different data elements, we spent a lot of money on engineering and resources in order to be able to do that. And so if you look at it on paper, it didn't make any sense. But if you look at the long-term vision of where it needs to go, it does totally make sense, because the organization starts learning how to think like this. And that's actually the value that you can't put down into a Jira story. You have to actually understand that from the direction.
That's fair.
That sounds good to me. I mean, but you had an organization that was committed to that. So, what if you were in an organization that you wanted to bring this in and they didn't appreciate, they weren't thinking long-term like that? Like what are there any sort of cultural, and this is actually a real question, do you think there are certain cultural, elements or aspects of the organization, as well as sort of the tech stack or the infrastructure, that you would need to have in place first before mucking about?
Absolutely. And I think that's why there's so many people that move from role to role or job to job or company to company, is because the culture doesn't fit the idea of constantly getting better and thinking about what the long-term way to learn faster is, right? And so if you're not in a culture like that, then they're not going to be amenable to this. And they're not going to see the payoff right away. They're going to see a bunch of sunk costs, and you're going to have somebody who's going to be leaving in 2 years because they're not seeing the realization of what it really takes to put this together.
We have 2 minutes, and I have one question in the chat that I'd like to get to. And I also want to remind everybody that our next conversation is selecting the right KPI and experiment design in 2 weeks, February 16th. And still seeking panelists. If anybody's interested, reach out to me. And then we're also still soliciting topics for after February 16th. So feel free to reach out if you have them. But the last question that I want us to take is from Merritt, and he asked, what percentage of machine learning initiatives, and that probably, and I know we can't answer an exact percentage, but you'll understand, do you think are driven from like top-down executive requests based on faulty or naive understanding of the needs and benefits, and therefore can be cursed from the start? So in other words, they're saying, hey, we need to do machine learning, kind of like, I don't know, 5 years ago, it was like, we need to do personalization, but nobody really knew what it meant.
Yeah, so for me, that was sort of my point about, if you're ready or not. And I think if it's sort of fetishized, like it's just machine learning is what, so what Dylan was talking about, I think, not to put words in his mouth, is like, are you an organization that's trying to improve your process and you're looking for long-term improvement and you're willing to invest in that? That's one thing. Another is, hey, this is signaling our sophistication and we want to be also doing machine learning because that's the thing we should be doing in AI.
Bandwagon.
It's bandwagon, and it's like, it's like objectifying it, as opposed to we're trying to, what is a method for us to improve long-term, as Dylan was talking about, versus let's just do this thing, this theater of it, right? And so I don't know how often that happens. And I think that would be a question that the group would be able to answer better than I could. But that's what I'm afraid of, is that's the risk. And that's, I guess, what I'm trying to dissuade people from is just this jumping in without having given it a little bit of thought, and just that it's coming down from the top management who wants just to use it. That's going to be a disaster, I think.
I agree. Thank you, Matt. I really appreciate it. Thank you, everybody. If you have follow-up questions, jump in the TLC Slack, send emails to me, or I'm sure Matt would respond directly, right, Matt?
Yep. Everyone's welcome to send me any questions you have.
He's a nice guy. He's fun to talk to. Thank you so much. Really appreciate it,
Thanks,
everybody.
Kelly.